Hi, I'm Olivia, everyone's favorite math teacher, and in this video, we're finally going to talk about the Fundamental Theorem of Calculus. So here they are, two extremely important theorems that we're going to be using throughout the rest of the calculus curriculum. Now, the mean value theorem is very similar to the mean value theorem that we were talking about with derivative calculus, although this time for integrals. And it's the same idea, which is that if you have the beginning and the end of a continuous function on a closed interval, there's got to be a middle, and this tells us how we find it. Now, this time, because we're talking about an area, we're simply going to divide out that length that we were talking about, and that'll find us that midpoint. We'll see how that works in action in a bit. So, for the fundamental theorem of calculus, though, we have two parts because it effectively gives us two very important conclusions. The first one is that if we have a function that we take the integral of, and then we take the derivative of that integral, we get back to the original function. That means, effectively, that the integral and the derivative are inverses of each other. And that's pretty important because of the second part of the fundamental theorem of calculus, which tells us that when we're looking for a definite integral, we only really need to take the antiderivative of the beginning and the end and subtract them, and that will tell us what the actual integral is for the whole thing. That's pretty amazing. But interestingly enough, if you'd kind of been paying attention when we were working on this a couple of videos ago, you might have noticed that both of these two things were kind of happening when we were taking those limits. But why this is so powerful is because part of our problem was that we don't yet have the tools to take that limit of the summation for all of the different sums that we're going to do. For example, how do we take the limit of an infinite sum of a sinusoidal curve? Like, we don't necessarily know how to do that at this point in our calculus curriculum. So this will allow us to kind of circumvent that, but we need to prove that this works for any function that fits our criteria, and that criteria is important, that our function is continuous on our interval. You do need to always make sure that you're checking this, because it's really easy to slap the integral onto any function, put it on an interval, and say, hey, go ahead and integrate this. Because there's a lot of functions where, yeah, you can take the antiderivative of the function, but that function might not be continuous on the interval. For example, what if you have an asymptote right in the middle of your function? You'll get that with rational functions, for example. So you'll need to check those. Now, let's go ahead and get to these proofs. So here's the proof of the mean value theorem. And it might look a little daunting, but honestly, it's just a bunch of theorems that we already know, and a lot of things that really just make sense of something that conceptually is pretty straightforward. So what we're saying is that since f of x is continuous on our closed interval, there exists some minimum and some maximum that basically contains that function, okay? And that minimum and maximum are part of that closed interval, and also, and this is important for the bottom part here, they are less than or equal to the f of x. So that means that f of x also contains those points. That'll be very important. Now, if we take the integral of all of those pieces from our previous comparison version, we know that that's going to give us the lower bound is below the area of the function, which is below the area of the maximum. But then if we go back through and divide out that interval, well, that just gets us back to that m and that capital M. So that line here and that line here, which we knew that was just that point on that range, right? But now, this bit here in the middle, we're going to leave looking just like this. But this is simply a value. And this would be getting us back to here. And we know now, though, because of way back at the beginning when we talked about limits and such, that because this f of x is continuous on this interval, and it does contain this lower m and upper m, by the intermediate value theorem, we know that there's a c somewhere in the middle of those. So we're simply going to say that that f of c is this 1 over BA times that integral theorem. Now, again, this might seem like a big chunky mess, but really, when you look at it graphically and you kind of work with it with numbers, it does make a lot of sense. So let's look at an example really quickly. So here's our example. And the only reason it looks complicated is because I went ahead and did it in two different ways. Geometrically, because remember, if we look at this line, well, it just makes a triangle. And we know how to find the area of a triangle. But we also know how to find that same area using the limit definition of our integral. The problem, though, is that not all of our integrals are going to be as easy because we can't take this limit of every sum. In this situation, we could because this was just the first in integers. So that leads us back to our fundamental theorem of calculus, because remember that part 2 told us that we actually can find the definite integral of any integrable function. Whew, that is a hard word to say. So let's go ahead and take a look at those two proofs so that we will be able to do this with most functions. Okay, so here's our fundamental theorem of calculus part 1. Now, this proof looks really complicated and it's very mathy, but it's actually not very complicated because, again, we've actually learned all of these properties. We're simply putting them all to use in very specific ways. However, there are a couple of things that I want to point out here that maybe you don't necessarily notice notationally that are pretty important, okay? First thing is that we're talking about f of x being continuous on AB, and then when we look at this capital F, we're taking that interval being a to x. But because this f of x is continuous on AB, this x is any value from a to b inclusive. So that means that x could very well be that b, but it doesn't have to go all the way up to there. So that just gives us the flexibility of this property, being that we can take this derivative anywhere on that interval and this property remains true. So that's why we go a to x, okay? Furthermore, the reason we can do this with this f of t is because this is a definite interval. So we know that this is a value, even if we're using a t here, because we know that this function exists everywhere on this interval. Now, another thing here is I've had to kind of redo this part repeatedly because the word integral and the word interval are so similar, and I say them so many times during this proof that I get them mixed up a little bit. So if you hear me pause or you see me stop for a second, it's because I'm trying to make sure that I say the correct word at the correct time. Okay, so we have f of x is a continuous function on some interval AB, right? And then we have capital F being defined as a function such that it's the integral from a to x, that's our interval, of f of t dt. Now, we're going to take the derivative of it, and we're going to use our definition, our limit definition of the derivative. When we bring out the 1 over h here, that gives us just the capital F's here. And so we're going to redo this integral here, and we're going to use this x plus h as the upper part of our interval, and then this x as the upper part of our interval here. Now we're going to go ahead and use those properties we learned earlier, specifically the negative interval property, which allows us to convert this negative to a plus by flipping the interval over. So we had a to x because this was a to x, but then we're going to flip it to x to a. Now, what that does is gives us a lower a and an upper a. So then we can use another property that said, if we have the bottom of one interval the same as the top of the other, and it's a continuous interval, and the function exists across it, we can slam those intervals together into one integral. So we do that. And that's what we're doing here. I'm simply flipping them around to show we have the top here and the bottom here. Boom, we get one integral that goes from x to x plus h. Now, you might not realize why that's important, but here's why we want to do that. We have 1 over h, but 1 over h is the same thing as saying x plus h minus x, meaning x is the bottom of our interval, and h would be the top of our interval because we're going x plus h. So x is down here at the bottom, and then x plus h, h being the top. So what that does is lets us set up the mean value theorem, so we can now find some c that exists in between the x and the h. So as that h approaches 0, it squishes that c down towards the x. So because f of x is continuous and that c exists between the h and the x, what happens is as h approaches 0, f of c is equal to the same thing as that c approaching x of f of c, but as c approaches x of f of c by our limit properties, that means that that's just f of x. So if we put all of that together, we know that this is equal to this, but by the mean value theorem, that is equal to that, but by the limit property, that is equal to that, which means this is equal to this on our interval. Or in other words, on a closed interval, if we take the derivative of our integral, we get our original function back. Basically proving that the derivative and the integral are inverses on a closed interval with a continuous function. Pretty neat, and it took all of our calculus properties up to this point to prove. Let's look at an example of how we would use this, and then we'll get to the calculus theorem part 2. Now, remember, what we're talking about is taking the derivative of the integral. So when we're doing this up to some value x, all it's going to do is replace whatever our variable is in our function with whatever that upper limit is. However, whenever that upper limit isn't what it's supposed to be, or rather when it's not just a variable, we might have to use the chain rule in order to actually complete this situation. So on the top one, this is what I'm talking about. This is a complicated function, but it really doesn't matter because we're taking the function with respect to r. We have an r. So all we do is we just go, oh, well, it doesn't matter. We're just going to go ahead and convert this over, and boom, there we go. There's our derivative. But now when we look at our next one, we have a problem. We only can take this derivative when we're going from a up to x. So we actually need to use one of our properties to convert this so that we can use the fundamental theorem. And so we need to go ahead and flip it over. And so in order to do that, we simply apply our negative. And now we're running from 1 to x, so now we can apply it. And so we get our negative out here in the front. On this bottom one, we have an even trickier situation. And it's that we don't have an x. We actually have another function. So instead of just going up to x, we actually have a function that's kind of defining where we are within our function. So in order to do this one, we actually have to utilize the chain rule. However, remember that when we're doing the chain rule, it's supposed to be, in this case, it'd be dg du and then du dx. But our dg du is simply, in this case, 3t with respect to here, right? So when we take that first part of our derivative, that's just going to be taking this function and putting it in place of where the t is. So 3 times x squared. However, when we do the second part, we will need to go ahead and take the derivative here. So there is a little bit of work to do using our chain rule. And so that's going to be the derivative of x squared, which is just 2x. And then if it's something we can do to complete that, we do. So in this situation, our derivative of 3t from 1 to x squared would actually be 6x cubed. A little bit weird, but that's because this situation is a little bit weird. And finally, we have the Fundamental Theorem of Calculus, part 2. This is the part that allows us to take the integral of a function that we otherwise wouldn't be able to because it gives us a slightly tricky infinite sum. So we're going to start by having a continuous function on an interval ab, just like all of our other integrals. And then we're going to have f of x be any antiderivative of f of x. Now, I'll explain why that works when we look at the examples. So P is going to be any regular partition of AB, and specifically all that does for us, or what's important there, is that A is going to be equal to x naught, and B is going to be x of n, and this is going to be broken up into an equal number of partitions. Any number of them, it doesn't matter, right? So thus, f of b minus f of a is simply going to be x, or f of xn minus f of x naught, and then this can be rewritten as the sum of those partitions, which we're going to rewrite in summation notation. So because f is an antiderivative and it's continuous, we know from the mean value theorem that we can find some c sub I for each of those partitions. And we're going to use the actual ends of those partitions as our interval. So what that allows us to do is replace this part with f of ci delta x, where the delta x is that interval. And because when we get down to here, we're going to be taking the limit as n approaches infinity, we're going to be shrinking the size of those partitions down to just that point. So this c sub I is going to be approaching x, just like we showed in our previous proof. So what effectively happens here is we're able to then say that f of b minus f of a is equal to the summation with the f of ci delta x. Then when we take that limit, nothing really happens here because there's no n, but here that becomes the integral, and like I said, this f of ci becomes f of x, and then of course our delta x becomes dx. So we get that f of b minus f of a is equal to our integral of f of x dx. Let's go ahead and look at an example. So applying the second part of our fundamental theorem of calculus, we're just going to be evaluating some integrals. Now, our first one is a simple polynomial, which means we're just reversing the power rule. So we find our antiderivative of each piece, and I went ahead and used the plus c here because, like I said, I was going to demonstrate why we say any antiderivative works on the definite integral. And it's because when we take the difference, that c exists on both parts, which means it gets subtracted away, which means it doesn't really matter. So when we go ahead and do this difference here, we take the lower bound, which happens to be 0 here, so this side is just going to be 0. That doesn't always happen, but it did here. And then we take the upper bound, which here ends up being 1 plus, and this is 1/10, and this is minus 1/25th, and so we end up getting 1 and 3/50ths, so 1.06. Now, on our second one, it's a little trickier to find the antiderivative, and you can probably look it up in a trig table, but I went ahead and just worked it out the way that I was talking about when we were talking about antiderivatives. And what I noticed was that when you look at the secant times the tangent, well, that's just sine over cosine squared. And anytime you have something squared in the bottom, that makes me think, okay, this is probably like a quotient rule situation. And it turns out that, yeah, that's exactly what it is when you apply the quotient rule. So that tells me that the antiderivative of secant theta tangent theta is just secant theta. So going ahead and applying that antiderivative, we get that we're looking at the secant of pi over 4 minus the secant of 0. And because secant is just 1 over cosine, that tells me that the secant of pi over 4 is 1 over square root of 2 over 2, which is just the square root of 2. So this is square root of 2 minus 1, which is roughly 0.41. So I'm going to leave you with a couple to try yourself, and then we'll go to the outro. So I hope you found this introduction to the mean value theorem and the fundamental theorem of calculus helpful. If you have any questions, feel free to drop into the comments or join us on Discord. And as usual, the answers to the exercises will be after the outro.